Our next speaker is Zach Lipton. He is Assistant Professor of Operations Research and Machine Learning at Carnegie Mellon University. He's here to tell us how to use NLP and machine learning to build summarization models. Please welcome Zach Lipton.
Hey everybody, my name is Zach Lipton. I am a professor ostensibly at Carnegie Mellon University. My primary positions are in the operations research group, which is part of the Tepper School of Business, and operations research is generally the science concerned with optimal decision making. And my other primary academic post is at the machine learning department, which is actually my sort of native discipline, where I well, you know what machine learning is, so let's get on the road. I run a group called the Approximately Correct Machine Intelligence Lab. The name is a little bit of a play for us on a couple things. First, there's approximately correct, the sort of like key sort of mathematical paradigm for the theory of learning and generalization. So when you're trying to not solve analytically for a function, but to approximate it based on some finite number of examples, some experience you have interacting with the real world, you can almost never just say like, oh, this is exactly a model that is always correct, but rather you want to make some kind of statement that if I have at least so much experience, then I am, with high probability close to the truth. But for us, some of us work on theory, many of us don't in the lab. The name takes on another meaning, which is that the way machine learning is used in the real world is very often only an approximate solution to a really complex real world problem. So there's a different kind of approximation which is happening here, which is not due to finite samples, but due instead to the fact that there's a bit of a mismatch between the formalism and the technical framework that we have for solving problems with data and the real world problems we're trying to solve. For example, one that I'll talk about a lot today is this gap between decision making and pattern recognition. Where often we have mature tools now that are starting to work in real world data sets at magnificent scales for pattern recognition, but it's not always so clear that can actually guide real world decision making. So predicting what would happen to you if you're given the drug that you always would have been given is not the same thing as predicting what would have happened if someone assigned to you a different drug than ever would have historically been done. So these kinds of things, what would happen if I made different decisions? This starts getting into the science of decision making, and in particular causality. Moreover, making decisions in the real world where the real world is actually changing. So the fatality rate for coronavirus is not the same as it was now, as it was 6 months ago, as it was 1 year ago. All these kinds of things of dealing with sort of distribution shift and robustness against kinds of ways that the world in subtle ways around us. These are all sort of primary focuses of the research in my lab. And of course, another way in which machine learning is often only an approximate solution to problems is that we're usually optimizing some kind of quantitative metric like accuracy or the AUC for some specific well-formulated prediction problem. But we also have a whole bunch of other sort of categories of desiderata considering how our automated technology impacts people in the real world. And these are often much more difficult to quantify. So we do a lot of work thinking about the sort of social and sort of ethical sort of import of the technology that's being developed around us and sometimes by us. So high level, this talk I'm focusing on machine learning in healthcare, and talk about focus a bit on NLP, but I'd like to kind of just start off with, at the outset, a high level view for, the field as I've experienced it. And, there's other people who've been in the field much longer than I have. But, I've been here for a sort of during interesting times, really seeing the field change dramatically from 2013 when I was first starting my PhD to now in 2021 as I sort of go into the maybe second leg of my faculty career. So, what I've seen sort of at a high level is, machine learning started off machine learning in healthcare as a kind of simple practice of there's a bunch of guys over there in machine learning who've developed these cool models. Some of them work a little bit better. Some of them work a little bit worse. some work better on some data sets and worse on others. Let's come up with medical problems where there's something we'd like to predict. Usually this was relatively simple data. So most of the time, like tabular data. By tabular, I just mean, there were a few features characterizing each example, and you sort of dump it into your list of machine learning models and say, how well can I predict this thing? I kind of entered the field as there was a shift from sort of this simpler approach to these fancy new tools like deep learning, where suddenly we were able to deal with much more complicated kinds of data, like varying length sequences where the order of events in the sequence mattered, or multimodal setups where we're dealing with raw text and images and all kinds of other signals, and we wanted to combine them to make predictions. And we're doing, we've had a bunch of strides, although it seems like these are starting to become commoditized, and deep learning is becoming sort of, it's still sort of what it always was. Is well, I guess before it was something that was sort of wild and empirical and not so practical. Now it's something that's eminently practical, but still wild and empirical, and not something practice that's guided by all that much theory, which is another sort of area where we try to fill in some gaps in our lab, and a lot of my colleagues at CMU work on problems like that. The question is like, where's the future? Now we have these fancy predictive models, and the answer is sort of maybe twofold. And one big area that we work on that I'm not going to talk as much about today is how do we go beyond predictive problems to guiding decisions, and how do we deal with things like not just estimating conditional probabilities, but causal quantities. But then there's the other side, which is, there's still a lot of fancier yet prediction to be done for problems at sort of different scales and different length documents and different size we're trying to work with. So in particular, this talk, I'll be talking about text summarization, which is a challenge that sort of goes beyond the capabilities of the systems we were working with until now. So again, classical AI for healthcare is get some data, arrange it in a tabular fashion, columns or features, rows or examples, fit your sort of favorite machine learning model, off the shelf. So get some data, decide what are the features, decide what are the targets, throw a bag of models at it. That was the state of the world maybe in 2013 for most of the, what I saw happening in the like ML for healthcare type world. Of course, I'm painting too simple a picture, and there were other things, interesting things happening in like the computer vision side of things, but, give me some license. So deep learning came along, flexible models capable of handling high dimensional data, et cetera, et cetera, et cetera. Dealing with long and varying length time series, dealing surprisingly well with missing data without even sophisticated imputation strategies, like just doing simple things like saying, is this data here or not, and just representing that as like dummy features. And, on one hand, deep learning has sort of blown, on problems with enough data and with complicated enough structure that traditional models failed. It sort of really changed our abilities from a standpoint of just pure predictive, accuracy on a whole, variety of problems. And at the same time, there's sort of a slightly maybe perhaps ahead of the cart ahead of the horse type excitement about what this technology is actually done so far. So, there've been articles, position pieces arguing, hey, we've arrived at the time, and now's the time that we should be making the best treatment decisions based on, computationally learned sort of patterns in electronic health records. And it's like, whoa, we haven't solved the decision problem yet. We're sort of still on predictions. We don't really, there's a big conceptual gap between those things. So there's an interesting environment right now where the belief and the reality are maybe a little bit out of step in some ways. And at the same time, there are really significant breakthroughs. So deep learning has been used to diagnose diabetic retinopathy. It's being used to recognize abnormalities in various sort of photos of skin abnormalities. So, for example, this paper is about like dermatologist level classification of skin cancer. It's very important to take these claims with just a little bit of a grain of salt. In that, on one hand, yes, it's quite astonishing that we're able to perform better on some test set of images than perhaps a human dermatologist. And at the same time, the model's sort of validity is entirely predicated on the fact that the train set and test set are a random split from the same exact indistinguishable, underlying distribution. And on the other hand, the human, if you change the lighting conditions a little bit, or you encounter individuals with slightly different skin tones, the human's ability to recognize skin cancer isn't necessarily going to break, and humans in general seem to be quite adaptable. Models, on the other hand, are still, remarkably brittle. So, my first sort of foray into this area in terms of significant publications was working with Children's Hospital Los Angeles. So with my good friend now, at the time, I guess was a new acquaintance, David Kale, who's now doing exciting things with machine learning at Netflix and was one of the founders of the Machine Learning for Healthcare conference. Randall Wetzel, who was one of his mentors and is the head of the pediatric intensive care unit at Children's Hospital Los Angeles, and my advisor, Charles Elkin. And we got access to a bunch of data. It was 10,000, which at the time was like relatively large for a medical data set that we could get our hands on, given the richness of the data. It was 10,000 patient stays in the ICU. So when I say 10,000 data points, I don't mean 10,000 measurements. I mean 10,000 individual, patient checks into the hospital. They are there for some period of time in the pediatric ICU, and eventually they are either discharged or there's some of the patients die while in the hospital. And so basically from the beginning of the stay until the end of the stay, that is one episode. And for every patient, we have a whole bunch of frequently measured information, like their vitals, the information recorded on rounds, etc. And what we basically did was we were sort of in really the right place at the right time, that this technology was really new. Recurrent neural networks were a hot new tool for making sense of sequential data in the context of text, and there had just been some breakthroughs in machine translation and text classification. And we started saying, hey, well, what was wrong with what we were doing in text before is we were forcing the data into these tabular representations and then running linear models, but actually the order of the words really mattered, right? So it mattered if the sentence was virus kills scientist or scientist kills virus. These have very different meaning. And we thought, similarly, people were trying to represent whole patient trajectories in the hospital with some fixed length vector. And we thought, could we do a lot better if we actually adapted these RNNs? So we developed some procedures for representing patients, for dealing with missing values, getting these things to train. We came up with some clever tricks about how to apply the loss so that the model sort of at any given moment, given the available information, made sort of the most accurate prediction it could at that time. And so that was sort of our first foray in. I've also done some work over the years with a number of other collaborators, like recent work from a year ago with collaborators at the Cleveland Clinic, or I guess 2 years ago now. We figured out how to do a bit better at recognizing stages of development in embryos in the fertility clinics. They could do a better job implanting them. And the one thing that'll carry over to when I talk about summarization here is that it turned out that one of the tricks to getting a big performance boost was to first have the model extract the precise subregion of the image that actually contained the embryo, and only then to do the classification. And the tricky part of that is that nobody annotated for us what was the right region that contained the embryo in all the images. So the model has to indirectly learn by, if I pick the right region, then the classifier did well. And the classifier is just trying to do well given whatever the detector hands it. So, that's sort of a background on the state of and sort of evolution of a lot of work in sort of applying deep learning in healthcare and my history. And then I got to CNU as faculty, and I started working with this company called Abridge, collaborating with them as a sort of research partner over at CMU. And they were interested in this problem of dealing with doctor-patient conversation. So let me give you a little bit of context first. After every visit, doctors have to write up a semi-structured note that keeps track of a few important things, like what are the subjective things the patient reported, what are the objective findings at the visit, like lab tests and vital signs and physical exam findings, what's the assessment, so what you think is going on, and the plan for what you're going to do. And there's also some sort of informal finer subsections here, like subjective, right, might consist of chief complaint, history of present illness, etc. These tend to be 300 words on average. And compare that, to summarization tasks, where typically a summary for the CNN Daily Mail data set consists of 1 or 2 sentences. So doctors have to create these notes, and in the past they might have written their notes scribbled, on a pad while seeing the patient. But now doctors sort of face this interesting challenge of they either have to like dictate their note after the visit, or they have to type up the note, but they need to get into a digital format because of the advent of electronic health records. And oftentimes doctors end up getting overwhelmed and can't write the note during the day, and then they end up writing the note based on what they can recall once they're home at the end of the day, and sometimes forgetting details. Um, and so there's an interesting development in parallel, which is it turns out that patients are actually often recording their conversations with their doctors. And so they do this for a variety of reasons. I think a lot of patients do it because they waited a long time to see the doctor or the specialist, and they want to remember what they said, or they have trouble keeping track of it, or maybe they have a family member who helps them coordinate their care, and they want to share it with the family member so the family member knows what's going on. This is a phenomenon that's already at play. So this company, Abridge, basically had this idea of what if you normalize this sort of recording as part of the normal doctor-patient interaction. So people record their visit, and at the end of the day, there's sort of two hopes. One hope is that you could provide a whole lot of value to the patient directly by sort of identifying important moments in the conversation. This is where you talked about changes to your prescriptions. This is where you talked about the follow-up visit, etc. And at the same time, there's also the possibility that we might be able to eventually generate like a formal clinical summary, and potentially if there were buy-in on the other side from, if the doctors and patients were both party to the recording of the conversation, could benefit from getting sort of a first draft of a SOAP note that would maybe, have high recall for retaining important information. So our first step was we wrote a paper just seeing, can we even extract structured data from these conversations? So can we predict, what was the chief complaint, which symptoms were involved, et cetera, et cetera. And then, we did this paper, a little while went by, and then, I thought it was going to take us longer to build up the summarization, but at some point we just decided the jugular. And so the idea here is to actually generate a whole SOAP note from medical conversations. Basically, so we told you what SOAP notes are. Much of the information, although maybe not always every single piece of information that winds up in the note, is contained in the conversation. And these days, perhaps all the information is, or closer to all, because so many people are interacting with their doctors over telemedicine. So things that are communicated almost all have to be communicated out loud. And so the data that we got access to is basically a collection of doctor-patient conversations, where we have 7,000 conversations, 5,700 roughly, or 5,800 for training, 500 for validation. We actually have, but this was at the time of this paper that we developed. Each SOAP note we divide ultimately into the finest granularity of subsections. So so I should say what happened in this data set. We basically have real patient conversations where highly trained workers who are trained in the exact style and format of the SOAP notes drafted SOAP notes based on the conversation. So we know that the information in these SOAP notes is the information that is contained in the conversation. And moreover, for every sentence in the SOAP note, in what we could call the summary, the data set also doesn't just say, here's the summary, corresponding to that conversation. For every sentence in the summary, it's got pointers to here's where the evidence is in the conversation. So we have these like alignments that allow us to break up the task into a sort of cascade. So we explore basically, naively, you could just try to feed in the whole conversation into some neural network model and then generate the whole summary. The problem is, even with the biggest GPUs and the sort of like most powerful like servers that like an academic lab could like reasonably have, you can even hardly fit a single whole conversation into, say like a transformer model all at once. Moreover, you leave a lot of information on the table. You ignore the sort of granular annotations that we have that actually say, these are the important sentences and these are the corresponding important utterances and these are the corresponding sentences that they support. So what we did is we looked at this whole sort of spectrum of how to decompose this task. On one hand, there's the naive, just try to fit in whatever you can of the conversation and generate the note in one shot. Then we have another idea, which is say, let's try to first predict for every sentence in the conversation which sentences are important enough that somebody's going to cite them as evidence that should support some summary sentence. And so we first extract the like likely to be noteworthy sentences, and then we base the summary on those. A third, more granular step is first we predict which sentences in the conversation are likely to be cited as evidence for a summary sentence in a particular subsection. And we separately extract these for each of the subsections. And then based on each one, we generate the corresponding subsection. So as we're moving from left to right, there's an abstractive module which has to generate a summary, but its job is getting easier because it's going from generate the whole summary based on the whole conversation, generate the summary based on just the extracted sentences, generate the summary just based on just a particular subsection, and the far right, which turns out to be our best model, first extracts the per section sentences or noteworthy utterances, then it groups them into like little groups of 2 or 3 sentences that should go together to support the same corresponding summary sentence, and then the extractive module just needs to generate a single sentence. So we're getting near to the end of the time, but kind of here's the punchline, which is we have this approach, which turns out to be our best model. Extract the sentences, figure out which subsections they belong to, cluster them together, and then one cluster at a time, generate the corresponding summary sentences. And so we try all kinds of baselines for our extractive models. We look at all this sort of state-of-the-art abstractive models for summarization, including the sort of previous state-of-the-art to well-known pointer generator networks and modern approaches based on like T5 seek-to-seek models. So, you see we've got some neural network architectures for you to look at a slower pace when you pause this talk. And the takeaway is that the more we take away from the abstractive module, so as we go from conf to note to cluster to sent, we get better and better and better performance. So it says that there really is value if we want to approach these super complicated tasks and sort of finding the right way to modularize them into some smaller subtasks that are actually manageable. So you're not trying to ingest a 30-minute conversation and in one shot output an entire page long summary. So we look at a sort of overall performance, we quantify performance by subsection, and we have some qualitative analysis that kind of shows how this per subsection conditioning makes a huge difference in what pops out of our model. So this is all the time that I have. So thanks for watching my talk, and hope you enjoyed the conference.